Hi everybody. In this video I'm going to be going over the second midterm from my Physics 5C course in spring of 2024. There are some problems on here involving circuits, magnetic fields, and electromagnetic induction. And let's go ahead and get started on the first problem. So in this problem we have a circuit with a battery and some resistors. Now, the setup of the problem has one of the resistors described as an insulating container with some electrolyte solution. So we have some sort of conducting fluid, but we can still just treat this as a resistor. And that's connected to the circuit with a battery and with these two resistors. And we're given the resistance of the two resistors, and we're given the current through each resistor. We want to calculate first of all, the resistance of the electrolyte. Okay, so the strategy here is I know if I'm given these two currents, as long as I have two of the currents in the circuit, I can find the third one using the junction rule. Once I know what the current through this resistor is, I also know the voltage across this resistor because I know the voltage across R2. And R2 and the cylinder are in parallel with each other. So my strategy here for part A, my strategy for part A is going to be find current with the junction rule. Okay. And then voltage we can get from the parallel resistor. And then finally Ohm's law is going to let us get the resistance. Okay, so if I apply the junction rule here, let me label the current through this resistor I3. Okay, and I have this junction at the top where I have I1 going in, I2 going out, and then I3 going out. So I have I1 equals I2 plus I3. Okay, now we have two junctions in the circuit. We could have used either junction and we would get the same junction equation because this current from the battery I1 is entering this junction here. It's branching off into I2 and I3, and then those are joining back up at this junction at the bottom. So either junction would work. We get this equation. And we can go ahead and calculate what I3 is now. So I3 is going to be I1 minus I2, and we know both these numbers, right? I1 is 3 amperes. Apologies for the helicopter. I1 is 3 amperes, I2 is 1 ampere, which means that what's left over is 2 amperes. That's our I3. And now we can, now that we have that current, we can get the voltage across R2 using Ohm's law, because we know R2 is 3 ohms. Okay, so we're just taking 1 ampere times 3 ohms, so we get a voltage of 3 volts. And that's the same voltage as our electrolyte. Let me label this R3. Okay. Again, we have the same voltage. The delta V3 is equal to delta V2 because these two resistors are parallel. So I have delta V3 is I3 R3, which is the same 3 volts, which means R3 is delta V3 over I3, so that's 3 over 2, or 1.5 ohms. All right, so that's the answer to part A. Now we're told, suppose the cylinder is 10 centimeters long, has a radius of 2 centimeters, and is completely filled with the electrolyte. What's the resistivity of the electrolyte? So this is just using our formula for relating the resistivity and the resistance. Okay, we're told L is 10 centimeters, and the radius is 2 centimeters. Okay, our area, it's a cylinder, so the area, the cross-sectional area is the area of a circle. So it's just pi r squared. Let's go ahead and calculate that. Okay, I get this number, 1.26 times 10 to the minus 3 square meters. And I just want to rearrange this to get the resistivity rho. So it'll be R times A over L. So that's 1.5 times our area divided by L. All right, and I get this number, so 0.019 ohm meters. Okay, which is a relatively high resistivity for a conductor, right? If we were to compare this to something like copper, this is a very large resistivity, but compared to something like seawater or another electrolyte solution like that, this is a pretty reasonable answer. Okay, finally, at what rate is electrical energy being dissipated to thermal energy in the electrolyte? Well, this is just asking us to use I squared R, right? What rate is energy being dissipated? That's asking for the power. And well, that's just plug and chug, right? We have the current, which we said was 2 amperes. We have the resistance, which is 1.5. So this is just uh, 4 times 1.5, which is 6 watts. Okay. So I think maybe the only tricky part about this is realizing that we're not given the EMF of the battery, right? But we still have enough information in this circuit because we can use the junction rule and we can use the fact that these two resistors are in parallel to get everything we need to know about the electrolyte resistor. Okay, moving on then. Here we have a problem involving a magnetic field. So the magnetic field created by a current, in this case a solenoid, as well as the motion of a charge moving through that magnetic field. So we're told we have a magnetic field produced by a long solenoid with a certain diameter of 10 centimeters, right? So radius of 5 centimeters. And it has 2,000 turns per meter. So N is 2,000 per meter. Okay, and it's carrying an 80 milliamp current. Okay, and we're given the direction of the current, so we're told that the current flows, when we view the solenoid this way, the current flows counterclockwise. We want to find the magnetic field strength of the solenoid. So this is just plug and chug. Okay, we just have our formula for the magnetic field inside a solenoid, mu naught n times I. And we can just plug in, right? We have I, we have n, and mu naught is constant. Which I actually need to look up. I can't remember. Okay. Yeah, I can never remember if it's 1.26 or 1.27. So it's 1.26 times 10 to the minus 6. Not that that level of precision really matters, but... Okay. And it's, let's see if I can remember the units. Tesla meter per ampere. Yeah. Okay. Right, so we can just plug in. Current of 80 milliamps. All right, and I get this number. So 1, 2, 3, 4. So it's about 2 times 10 to the minus 4 Tesla. Right, or about 20 microtesla, or 200 microtesla. Okay, and then the problem asks, is the field directed into or out of the page? So this, we just use our right-hand rule for loops. Right, remember that says we curl our fingers in the direction that the current's moving, and then our thumb is going to tell us the direction of the magnetic field. So in this case, we just need to curl our fingers counterclockwise. My thumb points out of the page, and so that's the direction of my magnetic field. All right, that part is pretty straightforward. Part B, we have an electron that passes through the solenoid at a given speed, traveling perpendicular to the magnetic field. So it's moving into the solenoid like this. And we want to know what's the radius of the circular path the electron follows while in the field. Well, this is just asking us to calculate the cyclotron radius. Which is this thing. And again, this is just plug and chug, right? We have the mass and the charge of the electron. We just calculated the magnetic field, and we're given the speed. The speed was 1.6 times 10 to the 6. So we can just plug in. And then this number. Okay. All right, so I get 4.5 centimeters. Okay, that's all we need to do for that part. All right, now part C, we need to think a little bit here. So it asks, which of the following diagrams best represents the path of the electron as it travels through the solenoid? So they give us 4 options, A, B, C, and D. And we want to choose one of them. So it's multiple choice, but we need to explain how we made our choice. Okay, so we can't just guess. All right, so there's 2 things we need to decide here. Number 1, we need to know the direction that the electron is going to be deflected. So let's think about that first. You can see that of our 4 options here, there are 2 options where the electron goes right after entering the solenoid, A and C, and there's 2 options where it goes left after entering the solenoid. Those are B and D. So we can eliminate 2 of the options if we figure out which direction the electron moves. And for this, we can use our right-hand rule for the force on a moving charge, right? The right-hand rule for the cross product. Okay, so in all the pictures, notice the velocity, the initial velocity of the electron points up, right? It's entering the solenoid from the bottom, moving up. So that's going to be our V. Okay, and we said that B was pointing out of the page. So if we use the right-hand rule here, then we point our fingers along V, which means we point them up. We curl them in the direction of B, which is out of the page, and our thumb points to the right. Okay, that's our V cross B. But then because it's an electron, the charge is negative, so we need to flip it. Right, so the actual force on the electron initially, when it first enters the solenoid, is going to be to the left. Okay, so what that means is as the electron enters the solenoid, right, it's going to be deflected initially to the left. Okay, something like this. All right, so we know it's not A and it's not C because B and D are the ones where the electron goes left when it enters. Now, how do we decide between B and D? Well, that has to do with the radius of curvature of the electron's path, right? You can see that for D, the electron is not deflected very much at all, right, relative to the size of the solenoid. Remember, our solenoid has a diameter of 10 centimeters, so a radius of 5 centimeters. So what D is suggesting to me when I look at it is that the radius of the path is much larger than the radius of the solenoid that the electron is passing through. Okay. For B, here the radius of the electron's path, that seems to be, roughly comparable to the radius of the solenoid itself. And, well, the radius of our solenoid is 5 centimeters, and the radius of the orbit, the cyclotron radius, is 4.5 centimeters. So these two, the cyclotron radius and the solenoid radius, big R and little r, are about the same. Right? Or at least they're, one is not drastically larger than the other. So that means in our picture, we want to pick the one where the radius of the orbit and the radius of the solenoid are about the same. And that's going to be B. Okay, so that's our answer. Our electron moves left initially. And the radius of the cyclotron motion is about the same as the radius of the solenoid. All right, finally, problem 3. So this is a problem involving an RC circuit. So we have a circuit with a resistor, 2 ohm resistor, and a capacitor, which is 4 millifarad. And they're connected in series in the circuit shown below, right? So just a resistor and a capacitor connected. And this problem also involves electromagnetic induction. So we have this circuit is inside a external magnetic field, and the field passing through the circuit is changing steadily. Okay? The problem says it's been steadily changing for a long time, and the charge on the capacitor has reached a steady value of 1.6 times 10 to the minus 8 coulombs. That's our initial charge. Okay, and the problem also tells us, and it's labeled here in the picture, the top plate of the capacitor is positively charged, the bottom plate is negatively charged. Okay, so, ordinarily, if we just had a charged capacitor connected to a resistor, then the capacitor would discharge. But the changing magnetic field here means that we have an EMF due to the electromagnetic induction. So that EMF is, initially it charges up the capacitor to this charge Q naught, and then because we still have that EMF, because the field is constantly changing, steadily changing, the charge stays on the capacitor, as if we had a battery connected to the circuit. All right, so we want to use that. First of all, we want to figure out, so part A is saying we have a single loop with an area of 0.04 square meters. That's the area of this loop. Okay. What's the rate of change of the magnetic field strength? Okay, well, to figure this out, we first can calculate the voltage across the capacitor. We know that when the capacitor is fully charged, the voltage across the capacitor is going to be equal to the EMF that is, maintaining the voltage on the capacitor, or that charged it up. So our delta VC is Q over C. We can calculate what that voltage is. Okay, so I get 4 times 10 to the minus 6 volts. Okay, and this is equal to our induced EMF. Because again, that EMF, that induced EMF, is what is pushing charge and holding charge on the capacitor. So to get the induced EMF, we can use Faraday's law. Okay. So Faraday's law says the induced EMF is N d phi dt. Now N is the number of loops in the circuit, and the problem tells us we just have a single loop, so N is equal to 1. Phi is our magnetic flux, B times A, and the area is not changing here. The area is constant, so when we take our derivative in Faraday's law, okay, in fact, I'll drop the N because N is just 1. So this is dB times A dt, and the A comes out of the derivative, so this is just A times dB dt. All right, and well, we know the induced EMF because it's the same as the voltage across the capacitor. We know the area because the problem tells it to us. And the problem is asking, what's the rate of change of the magnetic field strength? Well, that's what we have here, dB dt. So we can just plug in. So we take our voltage, 4 times 10 to the minus 6 volts. Okay. And we divide by our area, which is 0.04. Okay, and I get 1, 2, 3, 4, so it's 1 times 10 to the minus 4 Tesla per second. Okay. Part B asks, is the field strength increasing or is it decreasing, and how do we know? So here we need to use Lenz's law. And the way I would think about this is we know our capacitor. Let me draw this out a little bit larger. So let's think about when the capacitor starts out initially uncharged. It's initially uncharged, and then we start increasing the magnetic field. Okay, or I guess we don't, we don't know, we start changing the magnetic field. We don't know whether it's increasing or decreasing yet. We start changing the magnetic field, and the capacitor charges up with positive charge on the top plate and negative charge on the bottom. So what's happening is positive charges are being pushed around the circuit this way by the induced EMF. Okay. In other words, we've got a current that flows counterclockwise like this. Okay, pulling charges off the bottom plate and pushing them onto the top plate. All right, now Lenz's law tells us how to find the direction of the induced current if we know how the magnetic field is changing. So we want to take Lenz's law and apply it in reverse to figure out, given that we know the direction of the current, and given that we know the direction of the magnetic field, right? The field points, was that out? Yeah, the field points out of the screen, right? How does the field have to be changing to give us this current? All right, well, we know if the induced current is counterclockwise, like this, right? The right-hand rule for loops tells us that our induced field has to be out of the page. All right, so our induced magnetic field is out of the page. Our initial magnetic field is also out of the page, right? And in order to get an induced field that's in the same direction as our initial field, we need the field strength to be decreasing, right? Because Lenz's law tells us that this current is trying to compensate for the decrease in the magnetic field by producing an induced field in the same direction. So since B induced is in the same direction as the initial field, the field strength must be decreasing. Okay. So let me just walk you through that again in case you didn't get it. Number one, we know the top plate of the capacitor is the one being positively charged. So that means current has to be flowing around counterclockwise to push positive charge onto the top plate of the capacitor. So we know and that current, the only source of that current is from the magnetic field, from the induced EMF. Right? So that's our induced current. And then we know that the induced current and the induced field are related by the right-hand rule for loops, right? So if we have an induced current that's counterclockwise, that's creating an induced field that points out of the page. Finally, since the induced field is in the same direction as the field we started with, which is given and the problem is out of the page, that means the field strength has to be decreasing, right? Because that's telling us that the induced field is trying to compensate to maintain the same magnetic field we started with by pointing in the same direction. Okay. Then part C, if the magnetic field stops changing, so now if the magnetic field stops changing, we no longer have the induced EMF, right? How long does it take the capacitor to discharge to half of its initial charge? And says we can assume the EMF becomes 0 instantaneously. Okay, so this is basically saying we switch off the EMF, now we just have a resistor and a capacitor connected, so we have a discharging RC circuit, discharging capacitor. And we know in that case, Q is equal to Q naught times e to the minus t over tau, right, where tau is R times C. Okay, so let's go ahead. We're going to need to know what tau is, so let's calculate that. R is 2 ohms, and C is 4 millifarad. Okay, so tau is 0.008 or 8 milliseconds. Okay, and we're looking for the time for the capacitor to reach half of its initial charge. So we want Q of t to be equal to Q naught over 2. And I can cancel the Q naught here, and I just have 1/2. Let me write it like this. So I have e to the minus t over tau is equal to 1/2. And I'm just solving for t here. So I'll take the natural logarithm of both sides. And then just rearrange to get t. All right, so if I plug in, so it's just minus 8 milliseconds times natural log of 1/2. I get this number, so about 5.5 milliseconds. All right, and that's that. So let me know if you have any questions about this. Let me know if you have any feedback on this video. Hopefully this was helpful, and I'll see you when I see you. All right, take care, everybody.